Without much further to do, let's just talk about a few things about the homework problem that you turned in. So you can't write on the thing because you've already turned it in, right? So this is something just to, I'm not sure if you remember what you did. But anyhow, the first question had to do with working with the FEV data set, that the data set on just one group of 40 kids who were observed for 5 weeks during a pollution, there was a pollution alert going on. And what you basically had to do was do the same analysis we did before, but change the reference group to week 1 as opposed to week 5. And when you did that for whatever marginal models you were going to use, one of the strong recommendations I've made, that anytime you're using a marginal model, the degrees of freedom, the denominator degrees of freedom for the marginal model, where you're not putting any random effects in the model, should be the residual degrees of freedom, which in this case there were 200 total observations, 40 kids times over 5 weeks, and then there were in the model that just had the 4 dummy variables for the 5 weeks, regardless of how you defined them, whether it was week 1 the reference group, which is what you had to do, or week 5 the reference group. There are 5 parameters, so you subtract 5 from 200 and you get 195. So that should have been the denominator degrees of freedom in the any marginal model you used. And if there was a random effects model where you were having 2 random effects, then you subtract from the 195 40 minus 1, or 39, for as many random effects as you have. If you have 2 random effects, it would be 39 twice, and so you'd get a reduced degrees of freedom for the random effects models. Now, in order to change the reference group to week 1, when the week variable was coded 1, 2, 3, 4, 5, there are a number of different ways to do that. And some of you may have done it different ways. Well, one way to do that is simply define a new week variable by defining it as 6 minus the previous variable. The previous variable is week, defining 6 minus week. What will that do? What will that do? How has that changed the new week? The old week variable is 1, 2, 3, 4, 5. If you do 6 minus week, what do you get? You also get 1, 2, 3, 4, 5. But now 5 means what? It means the first week, right? So you've reversed things around, okay? So if you do that and you put in your model a class variable, because this is how it's now defined. I'm still defining, this is still a class variable, or at least if you put in a class variable for week new in your code, then you run the model FEV equal to week, or week underscore new, then you will automatically get a contrast that you already get a chunk test for the overall comparison of the 5 mean FEV scores, automatically, because you've put in a class statement and all that. Now, so even though you've changed the coding so that the coding is now the first week is the reference group, by changing it this way, you don't have to write any extra contrast statement if you're using a class statement for this new coding, okay? But you do have to use a contrast statement to test for the average FEV scores if you decide to code, use dummy variables to code this, to reflect the new coding that you've done. So now one other thing is you notice that if I wrote the statement, here's the statement: contrast change week new. That's the new way I'm defining this new class variable. And if I did minus 0.25 like this 4 times with a 1, this will test the difference between week 1 and the average of the other 4 weeks. Is that correct? And tell me why. I'm just trying to make sure you know why this will do that. Why will this test, it's a contrast statement, so it's a test. Why will it compare week 1 with the average of the other 4 weeks using this new way of coding? I'm just trying to make sure you got this. Okay, somebody? You know the answer, you're just humoring me. Or you don't know the answer. Why does this work? Does it work? Why does it work? Why should there be a 1 over here and minus 0.25? What is 1 minus 0.2? It means something minus the average of the other 4, right? That's what it says. So why is the 1 here in the fifth thing, the fifth number, rather than the first number, where it was previously when the reference group was week 5? Because we've now changed the coding, so the reference group is week 1, and it's the fifth thing in the new statement. So that's why that gets a 1 over there, and it's minus 0.25. Got that? I'm not sure, but this is something, as you work through ProcMix and the other programs that you're going to be learning after this, you got to get more and more comfortable with this. So I'm going through some of these examples. Now, using dummy variables, W2, W3, W4, W5, this means that you're not using if you don't use a class statement, and you define W2, W3, W4, and W5 to be dummy variables that reflect weeks 2 versus week 5 compared to week 1, then I've got 2 contrast statements written over here. Now the first one says W2 1, comma, W3 1, comma, W4 1, comma, W5 1, degrees of freedom of 9. What's that testing? What's that testing? You tell me. Is this hard, or you're not sure? I mean, and one reason why I'm having you do the homework is so it's a contrast statement, so it's testing something. Is it doing a chunk test, or is it testing for a particular contrast? That's what I'm giving you a hint there. Is it testing for a given linear combination among the means, or is it doing a chunk test for the averages? How do you know it's a chunk test? Well, because it says chunk. But why is this a chunk test? And what is it testing? And why is it testing? Why is it a chunk test? Because what you see is W21 comma. When you see the commas in a contrast statement means you're doing several of these new variables in a chunk. So that's why this is a chunk test for whether the 5 overall mean FEV scores are all equal. That's what this is a chunk test for. Questions? So why is it so quiet? Because this is old hat? No, it's not old hat. I'm not sure what's going on here. So what about the second one? What's that testing? Is that testing something, or is it estimating something? It's testing something because it's a contrast statement, so it's a test. Is it a chunk test? How do you know it's not a chunk test? Because there's no commas, right? So what is it testing? Well, the way to figure out what it's testing, now what's weird is it's W21, W31, W41, W51. So it's testing whether the coefficient of the W2 variable, dummy variable, the coefficient of the W3 variable, W4 variable, it's the sum of these. It's beta 2 plus beta 3 plus beta 4. The reason why it's plus is because there's no comma, and it's beta 2 times 1 plus beta 3 times 1 plus beta 4 times 1 plus beta 5 times 1 equal to 0. That's what you're testing. Beta 2 plus beta 3 plus beta 4 plus beta 5 equal to 0. So what is that testing? Well, it turns out that if you actually do a little bit of algebra with this, recognizing the fact that now your reference group is week 1, not week 5. If the reference group is week 1, then beta 0 in your model has got to be the mean for week 1, because when you're in week 1, all the dummy variables are 0. You got 4 dummy variables, all those dummy variables are 0, and when you're in week 1, the only thing that's left is beta 0. So that's the reference, that's what beta 0 is. It's the mean for week 1, not for week 5. Different reference group. So that means beta 2 is the mean for week 2 minus the mean for week 1. Beta 3 is mu3 minus mu1, so on. Okay, and if that's the case, and you add up beta 2, because this is saying add up beta 2, beta 3, beta 4, and beta 5. If you add them up and consider the fact that beta 2 is mu2 minus mu1, beta 3 is mu3 minus mu1, and so on. Beta 2 is going to involve mu2, we're going to add mu3, mu4, and mu5, so there they are, mu2 plus mu3 plus mu4 plus mu5, and then you're going to subtract minus mu1 4 times, so it's minus 4 mu1. And then with a little algebra, you can factor out the minus 4 from this, and you wind up getting the expression that this sum is equal to minus 4 times mu1 minus the average of the other 4 means, which is what's being tested. That's why this contrast, when now the reference group is week 1, will actually test for whether the average of week 1 is different from the average, the week 1 average is different from the average of the other 4. That's how it works. Okay, so, and it turns out, it also will turn out that it's W21, but there are other equivalent ways you can actually do the same contrast. I could have written, instead of contrast change W21, W31, I could have, which is what I've written here again, I could have written W2 minus 0.25, W3 minus, what's the difference between the second line and the first line? That is, between this line and this line. I'm giving the same value for each of W2, W3, W4, and W5, but now I've changed it to minus 0.25 over here rather than 1. And now I've changed it a third way to 0.25. Why will all these three contrast statements really be testing the same thing? Well, the only way to see that is to work through the algebra for what they're doing. So, for example, you wanted to see what this second one, contrast with the minus 0.25s, is doing. It would be minus 0.25 times beta 2, minus 0.25 beta 3, minus 0.25 beta 4, minus 0.25, should have been a beta 5. It is a beta 5. Okay, and going to what the betas mean, plugging in that beta 2 is mu2 minus mu1, and beta 3 is mu3 minus mu1, and so on. If you work through the algebra, you can see that this sum of these four negative numbers, you might say, is equal to minus this expression, which is equal to the difference between week 1 and the average of the other 4 weeks. So if you use this contrast, you're testing whether this is whether this is 0. That's equivalent to testing whether this is 0, because this is just minus 4 times the same number. So you can often write a contrast in several different ways. So one of the things you have to get comfortable with is how you can write contrast statements to do various tests that you want to do. And I'm just showing you there are a number of different ways to do that. Okay, so that's, any questions on this? I'm not sure, but let me move on because it's really quiet. Let's see if I can get some other input here. Now, what if I asked you this? What is the correlation structure if you use this is for the FEV data, and suppose you had, again, 4 dummy variables for the 5 weeks, and your reference group was week 1. Could be week 5, but suppose it was week 1. Suppose you used a random intercept in your, when you defined your code. That would mean you'd have a random statement, and you say random intercept. And suppose you decided to use as your R matrix compound symmetric. So suppose you had a repeated statement where you said repeated, and then you say type equal to compound symmetric, and suppose you used a random statement with a random intercept. Now the question is, what would be the correlation structure if you did that? Now, one of the things we learned over the last couple of weeks is that if you had a random intercept, meaning the G matrix is just a scalar, is sigma square 0 for the single variance component, and you had an R matrix that was sigma square I independent, if you had a random intercept and you had the R matrix that was independent, what's the correlation structure? R matrix is independent, G matrix is reflecting a random intercept. Correlation structure is going to be compound symmetric, right? I'm not sure. Should we just start over again? I'm not sure what's going on here. It would be compound symmetric. Now, this question is asking something different. What's different about this question? Than what I just asked? I said, what if the G matrix, what if you have a random intercept and that the R matrix is independent? Then you can show, and I did some matrix algebra a couple of weeks ago to show that that would be giving you a ZG, Z prime plus R that's compound symmetric. Well, what would ZG, Z prime plus R be if the G matrix is still representing a random intercept, but the R matrix is not independent, but the R matrix is compound symmetric? What would ZG, Z prime plus R be? That's what I'm asking here. Now, in other words, I'm not using an independent R, I'm using an R that's different from independent, compound symmetric. How would it change? Well, the answer is, this is what the correlation, if you're using an R that's compound symmetric, this is what the correlation would be between any two observations on the same subject. That's the formula for it. Where sigma naught squared denotes what? What does sigma naught squared denote? It denotes the variance of the random intercept. And what's sigma squared denote? What's sigma squared denote? The variance of the error term. And rho, it would be whatever a correlation is between any two observations. And if you look at this formula, you notice that this formula doesn't involve either J or J prime. Right? So what does that mean? This formula, if you're talking about the correlation between any two observations on the same subject, this is saying that that correlation is the same, regardless of which two observations you're talking about. So what does that mean the structure has to be? If the correlation is the same between any two pairs of observations on the same subject, that means the correlation structure is it independent? No. Is it unstructured? No. What is it? Exchangeable. Okay, so I'm saying, if it turned out I varied the question by saying, well, suppose the R matrix is compound symmetric, it turns out that the V matrix, the ZG, Z plus R, also turns out to be compound symmetric. And on the next slide, I actually go through the matrix mathematics of that, which you don't really have to get through, so, except that I wound up working it out so that if the G matrix is sigma naught square and the R matrix is compound symmetric, that's another way of saying that the R matrix is sigma square times this exchangeable correlation structure. It's sigma square times this exchangeable correlation structure. That's what the R matrix is, sigma square C. And then if you actually compute ZG, Z prime, since G is just the scalar sigma naught square, you get this matrix. Everything is the same in this matrix. And when you multiply, when you add it to the R matrix, you wind up getting this ZG, Z prime plus R. Look at this matrix. Is that exchangeable or is it something different? Can you see that it's exchangeable? Well, that is, this is the V matrix. Can you see that it's a compound symmetric where everything, every covariance on the off diagonal is the same number. So it turns out that if you actually had a situation where you had a random intercept and the R matrix was different than independent, this situation where the R matrix is compound symmetric would wind up giving you still a compound symmetric or a correlation structure that's exchangeable. But what if it turns out, I said, what if the R matrix was not compound symmetric, but was autoregressive? What do you think the answer would be to the question, what would the V matrix be? That is, would the V matrix be compound symmetric if the R matrix was something different than compound symmetric? If it was autoregressive or unstructured, the answer would be it would be different. It would be different, and the way you'd actually be able to see that is use the VCAR option to make sure you see what it would be like. Okay, now, anyhow, that's just another point here. Now, let's see what I said here. What is the correlation structure if you use a random statement containing two random effects, like in that FEV example, with a repeated statement for either R equal to compound symmetric or AR1, R equal to AR1? Will it be the same as CS or AR1? Will it be more complicated? That's my question. In other words, what if it turns out you have a G matrix that's, if you had two random effects, G matrix is no longer 1 by 1. It's 2 by 2, right? Because there's two random effects. 2 by 2 matrix, that's a G matrix. And if you use R as compound symmetric or R as AR1, two different choices, and you compute V equal to Z, G, Z prime plus R, it turns out you won't get a compound symmetric matrix. It could be, the only way you figure that out is, by, sorry, I didn't mean to, is that it'll be more complicated. You'll have to use the VCAR option to see what you got, but it wouldn't be compound symmetric. The point I'm trying to make is that if it is possible to use proc mixed with an R matrix and a G matrix, you don't have to have just a G matrix with an R matrix independent. You can have two different kinds of matrices, neither of which are independent in the model. And if you combine them together, it's not necessarily you're going to get a compound symmetric overall correlation structure or covariance structure. It could be more complicated than that. And the way to see that when you've got both random effects and fixed effects in the model, the way to see what that covariance structure is or the correlation structure is to use the VCAR option. The VCAR option that we talked about. That'll tell you what the correlation structure looks like for that particular fit. Okay, now it turns out that for the FEV data set, when you're looking at that second objective, you've already turned this thing in, but when you're looking at the second objective and you've changed the coding from reference group being week 5 to reference group week 1, you should wind up getting exactly the same conclusions for which people were adversely affected by the pollution alert. It doesn't matter which way, it shouldn't matter what the reference group is in terms of what you're going to get, and it doesn't matter. So that's the main point. These other 2 points aren't that important, so I'm going to skip them. So let's talk about a few other things with the homework example. Okay, now in the homework example with question 2, maybe that was question 3, maybe there was a question, I don't know, the one thing was you had to run the FEV data set, and the other one is you had to do the gaze angle data set, which I talked about last time in class. Okay, and in the gaze angle data set, the extra thing compared to the shoulder flexion was there was this other factor, which was the Rater factor, right? The Rater factor. And the Rater factor could be considered either fixed or random, and what you had to do for your homework was to try to carry out the analysis if you used Rater as fixed, and also to carry out the analysis if you used the Rater as random. Now let me ask you, I'm not sure, when you had your lab yesterday, did you talk about all this? Zach? No. You didn't? Okay, so let me just, so when you're running this 4-way ANOVA model, why is it a 4-way ANOVA model? What are the 4 factors in the gaze angle data set? Day, time, Rater, and subject. Those are the 4 factors, okay? Now, if you're using Rater as a fixed factor, then it's a marginal model, right? If Rater is a fixed factor in addition to day and time, and you're putting in interaction with day and time, then you're dealing with a fixed model. Turns out when you try to run that fixed model, and I'm not sure how many of you did this, but when you actually run that model, you're going to see an error message, which is going to say, this model yields a non-positive definite G matrix and relate in an error message. So when you run that model, if you don't look at the log and you just run the model, you may think the model runs, but when you get this message, this means that model's no good. Because there's something wrong, the model's not fitting it. So what do you do when you get that? I talked about this last time. If the model doesn't run because you get an error message saying something's wrong, something's not positive definite, even though you think it might run, what do you have to do? You have to improvise. What does that mean? You have to start running subsets of that model by dropping some variables to get a model that runs. I don't know whether any of you did that, so that's one thing Zach's going to check when he looks at what you turned in. If you just ran that one model with the 4 factors in there and didn't look at the non-positive, didn't look to see whether you got this error message, then you didn't do it, you didn't follow through enough, because this is something you're going to get when you try to do your project. If you don't check this with your project, you're doing something incorrect. You'll be running a model that's no good, is what I'm saying. So, okay, so that's with the rater fixed. Now, when the rater's random, then I talked about a number of different ways you could write the model, and I showed you them last time, a number of different ways you could write the model. One way involved two random statements, and another way involved one random statement, and then I went through that. I went through that somewhere over here. This is one way you could have two random statements, and another way you could have one. I think you went through that in the lab, or did you not? Zach, I'm not sure if you did.
A little bit.
Maybe a little bit, okay. Because that's what last time I went through this, to say you can do treating rater as random. You can either use two random statements with subject equal to subject for the factors that were the interaction factors with subjects, but anything involving rater, if rater is random, shouldn't have subject equal to subject in there, because rater is a random factor, and if you put subject equal to subject, when you write rater, you're putting in a term that's rater times subject. You're not just putting in rater by itself. So you can write it like this without a subject equals subject statement, and you'll be doing an equivalent thing. Okay, so just trying to make that point here. Now, so let me just let me ask you some questions here. I'm skipping this. I'm going to the second thing. Look at these two codes. Going to on this slide here. Just look at these two codes, and you might want to look at your slides, but just look at them. The two codes. One of them has a model statement and a repeated statement, and the other one has a model statement and a random statement. Okay. So what's the difference between code 1 and code 2? Is there a difference? Are they both doing the same things, or are they doing something different? Are they both fitting the same model? Is code 1 and code 2, I mean, one has a repeated statement and one has a random statement, but are they both fitting the same model? And the answer should be no. Why? Because what is this assuming, or what is this assuming about the model? This. What's being assumed? That the correlation structure is compound symmetric, right? Isn't that what it's assuming? Isn't that what it's assuming? And it is assuming that time and rater are fixed effects, as is this statement. They're both assuming time and rater are fixed effects, but this one is assuming that the correlation structure is compound symmetric. What is this assuming about the correlation structure? Is it compound symmetric? It's very important that you got this distinction there. This is not compound symmetric. Why isn't it? Why isn't this compound symmetric? In order for this to be compound symmetric, how would I have to write this model to make it compound? How would I have to change it to make the correlation structure compound symmetric? What would I have to do with this random statement to make it equivalent to this, the output to be equivalent to it? What would I have to do? Anybody? Nobody? Again, are you just humoring me? It's not funny? Okay, what you'd have to do is, if you only kept random intercept here in this random statement, and you drop day times time, day times rated time, if you just used random intercept, subject equal to IDG, then you'd be fitting exactly the same model with the same correlation structure. If you only had a random intercept versus this is just what you know, is that in this case, there's no G matrix. G is 0. And the R matrix is compound symmetric. In this case, the R matrix is independent, and the G matrix, as is written here, is much more complicated than just a scalar for a random intercept, unless you drop all day time, rated times day, day times time. So code 2 is different from code 1. Now, what about the second question? Is code 2 better than code 1, or vice versa? If you had to do this analysis, would you do code 1 or code 2? Or why would you choose one versus the other? I mean, the whole, again, purpose of this course is to try to deal with correlation. So why would you might choose code 1 over code 2 or vice versa? What's the advantage of code 2 versus code 1, or the advantage of code 1 over code 2? Is there an advantage of one over the other? Well, the advantage is, I'm asking the question and answering it. Now, somebody, Tiffany, anybody.
It goes back to what you said in the previous lecture about whether your rater will change from like maybe study to study. If it's a fixed thing, then you might keep it fixed, but if it's a different rater each time, you might want to do that as a random.
Well, but now in both these models are models that are assuming rater is fixed. Can you see that rater is fixed? How do you know that rater is fixed in both these models? Because in the model statement, you see rater in the model statement. You don't put a variable that's random in the model statement. So both these models is treating rater as fixed. Okay. So the difference in the models is they're both actually having the same fixed effects in the model, but they're having different random effects. So the G matrix for this model is 0. The R matrix for this model, because it says CS, is compound symmetric. The R matrix for this model is what? The code 2. What's the R matrix for code 2? You don't see a repeated statement, so what does that mean the R matrix is? Independent. So what's the G matrix? The G matrix has, what's the dimensions of the G matrix? Is it 1 by 1 or is it bigger than that? Is it more complicated than 1 by 1? Well, it says it's 1, 2, 3, 4, 5, 6, 7. It's a 7, let's see, I got that right? 1, 2, 3, 4, 5, 6, 7. It's a 7 by 7 G matrix. It's not a 1 by 1 G matrix. So what you're doing for code 2 is you're allowing for a more complicated correlation structure or covariance structure. That's what code 2 is giving more than code 1. So is code 2 better than code 1? And you might answer, in one sense you might say yes, in another sense you might say it depends. If you say it depends, why might you say it depends? Why does it depends work? Well, if the correlation structure was truly compound symmetric, then code 1 would be better than code 2, right? Code 2 is giving you a much more complicated overall correlation covariance structure than code 1 is. So if the true covariance structure was compound symmetric, code 1 is better, okay? But why might not code 1 be better? Because do you ever know what the correlation structure is? And if you're not sure what it is, code 2 gives you more opportunity to find something more complex than you really may have. And it turns out what you could do is you could start with code 2 and then you could simplify it, and you might wind up with what's really equivalent to code 1 or something not quite that simple, but simpler. So the answer to the second question is code 2 is better than code 1 if you think about it. In fact, it gives you more options. It gives you more options for the correlation structure. Code 1 gives you a specific correlation structure. Okay. What about any other suggestions? How else might you do it? These are two ways to do it. This is the gaze angle data set. How else could you do it? Well, how else could you run, what's an alternative to code 1? What's an alternative to code 1? This was the gaze angle data set. Each person was looked at 3 days, 2 times, and had 2 raters. So they each had 12 observations. So what's another option for the correlation structure, covariance structure, other than compound symmetric? Unstructured, for example. You could have put in unstructured at a marginal model. So there are other options, I'm just saying. There's no particular specific correlation structure that you usually know in advance is the right one. That's one reason why this whole process is a little complicated. If you knew the correlation structure, it would be just one thing you'd put in, but you don't necessarily know that. So there were some other options. Another option is to choose a different covariance structure. But how do you know that the unstructured? How do you know that one of these is better than the other? What's another way to check that? Check to see if you're worried about whether you chose the right correlation structure. What's another way that we've talked about that in a previous homework example? Do the empirical option. Use the empirical. None of these things have an empirical option. What does the empirical option do? You would be on the first statement, proc mix data equal to GA empirical. You'd add that. What does that do? What does the empirical option do? It allows you to say, well, maybe I chose whatever my code is for repeating for the R and the G matrix. It allows me to say, well, maybe that's wrong. And it allows me to adjust something for the fact that it might be wrong. What does it adjust? Does it give you a different correlation structure? Does it change it from the R and the G you put in? No. But what it does is it adjusts the output, part of which is the standard error. In other words, you're getting estimates of the betas and the estimates of the standard errors, and it's going to adjust the standard error to try to reflect maybe there's something in the data that's is reflecting what the true correlation structure is. So it's doing some adjustment. And that adjustment may give you an answer that's better because it's correcting for the fact that maybe it's you chose the wrong correlation structure. So that's what the empirical option is doing. So you could use an empirical option here, and you could also use an empirical option here. And for any other thing that you use. Now, let me ask you this. If you use an empirical option here, and you use it here for two different sets of G and R matrices, when you get the adjustment of the standard error, is it going to be exactly the same? In other words, when you correct for the fact that this structure might be wrong, and you correct for the fact that this structure might be wrong, will the corrections of the standard errors always be exactly the same? Not necessarily. They might be exactly the same if you have a balanced design as this was. But if you don't have a balanced design, an unbalanced design, you can get different answers when you use this correlation structure for the adjustment than when you use this correlation structure and you use an adjustment there, because you're starting off with a different correlation structure to begin with. So that's going into play on what the adjustment is. It considers both what you started with and both what the true correlation structure is. So what am I saying about the empirical option then? Is it the empirical option solve everything? If you use the empirical option, are you done? The answer is no, because you can still get different answers if the original model that you did was used one correlation structure versus another. Okay, so anyhow, that's that. Okay, so that was this is my answer. Code 2 is better than code 1, not necessarily, but it does allow for a more flexible correlation structure, and this is what some of the questions. Now, we went through this. This is the next slide that I already showed you last time to show you how you might code how you might code the analysis if the rate was random. I went through this in two different equivalent things, and then I pointed out. I may have pointed this out. There's some questions about, say, let's look at this one. Both of these two are equivalent. Let's look at this one. Why not have a rater times day times time term in the random statement? Why did I stop here? Why didn't I also put rater times day times time? Why didn't I add that? Could I have added that? I can always write something. I can always write it and add it. What will have happened if I wrote that? If I added to this thing rater times day times time, then put a slash, what would happen? Well, the problem is I wouldn't be getting any errors. I wouldn't be getting any standard errors because I'd be perfectly fitting the model. Because everybody in the data set, every combination of day, time, and rater, there was only one combination of day, time, and rater. For any particular day-time rater combination, you didn't have two observations for a particular day-time rater combo. So you wouldn't be able to fit that model. You wouldn't be able to get any information because you need something to reflect the possibility that there's something left off. This would perfectly saturate the model. You wouldn't get anything. Okay. Is there anything wrong with the above code? Well, I've already asked that question. Is there anything wrong with the above code? The code is technically not wrong, but if you ran it and you found out that you got an error message saying that this model doesn't run because there's something wrong with it, then the code's wrong. The code's not wrong, but you're not getting an answer that you want to get. So you have to change things. That's what I meant. How do you evaluate the effective rate? Okay, third question. How do you evaluate the effective rater using the above code? What was the answer to that? I talked about that last time. I'm reviewing this stuff, but I think I needed to do it. How do you evaluate the effective rater using this code? Using this code, rater is a random factor, right? It's a random thing. Now, since rater is a random factor, how do you evaluate the significance of this random factor? When we talked about tests, evaluating the significance of factors, remember we talked about contrast statements, were statements that you could use to test for fixed effects? But what did you have to do if you wanted to do tests for random effects? What did you have to do? There were three choices. And of the three choices, what was the best one? This mixture approach. So if you wanted to test for rater, evaluate for rater, you could use any one of the three choices, the best of which was the mixture approach. The mixture method for evaluating the significance of it. That's what you'd have to do. So, for example, the answer, how would you evaluate the effective rater? You must use one or more of the methods for testing for random effects to assess for the significance of the rater variable, and must start with the highest order term involving rater in the second random statement. You can't just estimate. What I'm saying is you have to first, if this is your statement, you have to first test for this before you can test for that, because this is a higher order term. And you can do that using these tests for random effect, including the mixture test. So is there anything wrong with the above code? No. It's a good place to start, but unfortunately it doesn't give an appropriate answer when you actually look at the result because of the error message you get. So it's necessary to remove some of the variables. And then what I wound up doing was, I described this last time, and this is what you would hopefully have done in the homework assignment, run several different models and keep running them to see whether they ran. And none of these models listed on this screen worked, and the only model that worked was this one. So that was your final model in terms of what models worked. Are you with me on this? In terms of how you would do this? Okay, now, let me say a couple of other things. Once you got this model, if I wanted to use this model to test for the effect of rater, rate is a random factor. What I did last time, during the class last time, I talked about the three ways you did it. I illustrated the three ways you would test for rater, one of which was the mixture test, and that's what I did. I showed you what would happen if you fit this model. And you notice up here where it says intercept rater and it's got 0.2501. What is the 0.2501 doing? What's that giving you? What's that? Is that testing something? And what is it testing? It's testing the significance of the rater using what of the three methods? The walled method. Is that the best method? Not necessarily. In fact, so you'd have to use the other two, probably the mixture thing, and then what I then did in class last time, I went through how to do the mixture method. I went through it. So that's what this slide and these results did. That's what, and what happened was when I did it, I got different results for whether the rater was either significant. This is not significant, and when I used the mixture test, the rater thing was significant. The rater test was significant, which means I better use this thing and say I better keep rater in the model as a random effect. Better leave it in, not drop it out. That's what that said. Okay. Now, so that's all what we did last time using the mixture test. Okay. Now, let me just talk about a few other things, just to kind of go through, trying to do a few things that again emphasize some things here. Okay, so let's do this. Okay, here's some code. Some code on the screen. I got some questions. And this is the code. Some of you may have turned it in when you turned in your answer, but this is something that somebody did last year. They wrote this code, and they said, this is the code for a marginal model. Is that right? Is this the code for a marginal model? And the answer is, it's an easy question. If you had a midterm and that was the whole thing on the midterm, you'd get 100%. The answer is no. Why? Because there's a random statement in there. You know it's a random effects model. Okay. What is the G matrix for this model? What is the G matrix for this model? Now you notice it says, this is the tricky thing that people make this mistake. You notice it says random intercept type equal to UN. What does UN stand for other than United Nations? What does the UN stand for? Unstructured, right? Does that make any sense? What does the G matrix look like in this model? Is it a 2x2, 5x5 matrix, or what is it in this model? Random intercept. It's 1 by 1. It's just one variance component. That's what the G matrix is. 1 by 1, okay? So if you said unstructured, what would that 1 by 1 matrix look like? If you said compound symmetric, what would the 1 by 1 matrix look like? If you said AR1, what would the 1 by... It would be exactly the same matrix. There's only one term in there. There's only one estimate you're getting. It's not 2 by 2, which allows you to get different correlations depending upon how large the matrix. So this would be a misleading thing to write, type equal to unstructured. Some people do this because they get confused between the repeated statement and the random statement. Okay, there were 5 observations per subject, but when you put in a random intercept, there's only one parameter. So to put in type equal to unstructured is not using an unstructured correlation matrix. It's just still using a G matrix that's just it's still, for example, the G matrix in this case is just a scalar. What's the R matrix for this model? What's the R matrix for this model? No repeated statement, so the R matrix is independent, right? So what's the correlation structure, the covariance structure for this model? Given that we know the G matrix for this model is a scalar, single scalar, the R matrix is independent, what's the covariance structure for what this model is doing? What is it? G is just a scalar, the R matrix is independent, what is it? It's compound symmetric. Is it unstructured? Is unstructured the same as compound symmetric? No. So if you wrote this thinking you had an unstructured correlation matrix, you don't have it. This is compound symmetric. That's the code for compound symmetric. Okay, here's another one. Okay. Oh, there's the answer. This is the answer to all those questions. Does this describe a marginal model? No. What is the G matrix? A 1 by 1 scalar. What is the R matrix? Sigma square I. What is the V matrix? It's compound symmetric. Okay, here's another question. Okay, I've got some code here. Now you notice this code has repeated, doesn't have a random statement. The code, whoever wrote this last year, they're not here, so we don't have to worry about who they were. The code was given to test whether the average FEV score at week 1 was significantly different than the average FEV scores from weeks 2 through 5. Question A, does the above code test the comparison? Yes or no? How many say yes? How many say no? Well, that's nice, but when the no's were like this, what does that mean? How many say, I don't know? Nobody said, I don't know. So 3 people said no, nobody said yes, and nobody said, I don't know. So what does that mean? No. What? I don't know where I am. I'm not sure what planet I'm on today, something like that. I'm not sure, okay? So what does the above code test? You notice the commas over here? See those commas? So what is it testing? Is it testing whether there's a difference between week 1 and the average of the other 4? No. It's testing whether all 5 FEV averages are all equal the same. It's a chunk test for all 5 FEV scores because of the commas. How would you state the correct form of the contrast being considered? If you wanted to actually do this, what would you have to do? How would you change this to actually test whether the average of FEV scores for 1 is different from the average for weeks 2 through 5? How would you change what's written here? What would you do? I've already told you the answer in a previous slide. What would you do? You'd remove the commas. That's what you do. That's what you do. You just remove the commas from W21. You just or you could write W21, or you could write whatever number you wanted as long as it was the same number. That's what you could do. Okay. Now maybe am I just beating a dead horse here? I'm not sure. So I'm not sure. So let's do one more. Then I'm going to go on to something else because I got all these different things here. I'm just trying to get you to look at this one. FEV analysis. Okay, here's another code. Notice I did 1. If week is equal to 1, then I'm going to define a new week variable to replace this to be week plus 5. See that? Week plus 5. So this new week variable, if you were in week 1 for the first way it was defined, what's the value of this new week variable if you were in week 1? 6, right? Isn't that what it is? Week plus 5. If you were in week 1, it would be 6, right? It would be week plus 5. Okay. So if week is equal, but it only says if week is equal to 1. It doesn't say if week is equal to 2. So the only value I'm changing in that original week variable is the value for week equal to 1. I'm not changing the value if week was equal to 2, 3, 4, 5. Now I have a statement here, and I said, how does the above code transform the original week variable? What did it do to the original week variable? It changed the value of the week 1 variable to a 6, but it didn't change the values of the week 2, 3, 4, and 5. It's the same. That's what this says. It's just computer stuff. Will the transformed week variable treat week 1 as the referent group? How about that? Now I've got a new variable, a new week variable, and the new week variable is 2, 3, 4, 5, 6, right? And the values 6 correspond to what week? Week 1. So if I use this new code, would week 1 be the referent group? The original week 1 be the referent group? The answer is yes. Why? Because that's the highest number. The highest number of a variable that's a class variable is always the referent group when you're doing proc mixed. That's what, so I'm just trying to, will the contrast statement correctly test whether the average FEV score at week 1 was significantly different than the average FEV scores at weeks 2 through 5? Will it? I think the answer is yes. I hope so. Yeah, yes, because week 1 is the highest value for the week variable. Because what you've done by this new code, so there's a lot of ways you could change the code to change the referent group. And I've shown you some of this. And I don't know which ones you did. You could have done any one of a number of things. You could have done a whole bunch of them, but that's what, okay. So I'm going to stop with this. Okay, I'm going to stop with, I have other questions here, but I'm going to stop with this. Now, I want to go on to another topic. Okay, another topic. Okay. And it's a new topic. And it has to do with this. And this is something called the Durbin-Watson test. Let me get it up here in the top here. The Durbin-Watson statistic. Okay? I want to talk about that. It's a way of doing a test of hypothesis. Okay? And this is the reason why it's important to talk about this is because the whole business that we're dealing with is we're all worried about we got correlated data. And we want to do an analysis that reflects the correlation somehow. If we're able to know exactly what the right correlation structure is, we can put that in and say everything's fine. But we don't know that. So one thing we typically want to do is figure out somehow what the right correlation structure is. One way to do that is guess at it and think about what makes sense. Another way to do that is use an empirical option and hope that works. Corrects for the fact maybe it was the wrong thing. Another way to do that is to do a test for the correlation structure. And one of these tests, but we're going to learn some other ones after the break. We're going to learn maybe a little bit next time, next class. Another one is called the Durbin-Watson statistic. Okay. Now it's a test statistic. It's something you compute. So D stands for a value, a test statistic, some number that you compute that you use to decide some question about the correlation structure. That's what the Durbin-Watson is. This is new. Okay, this is just, and I put up a revised version of this slideshow of this presentation just a little bit before class. But this page didn't change. A lot of pages didn't change, but some pages changed. That's what if you want to use this test, that's what the test is computing. But obviously, what you want to have is a computer program to do it for you. You also want to know what are you testing? What are you testing about correlation structure? Okay, so let's talk about what are you testing? Okay, well this is what you have to do when you compute it. This is a table that's kind of complicated to go through, and I'm going to ignore that for now. So I'm going to go on to this slide. Okay, look at this slide. Okay, this slide tells you what's being tested by the Durbin-Watson test. Okay, okay, and it's one of there were other tests you can do, but until last year, this was the only test that was available to actually do a significance test for correlation. So there's stuff that's better now. We're going to learn after the break. But look, here's a correlation structure. Okay, here's the correlation structure. What kind of structure is it as you see there? Without looking at whatever, I've circled something or put something around an ellipse of some kind. But what correlation structure is this? Looking at it. Looking at what it is. What do you see here? All the correlations are allowed to be different, correct? They're all allowed to be different. Am I right? Row 1, 2, row 1, 5, row 2, 4, they're all allowed to be different. Okay. Now what I'm doing is what I'm now doing with this is so I'm showing you an unstructured correlation structure, and now I'm focusing on it's a 5 by 5 matrix. In other words, I'm talking about an individual that had 5 observations, 5 by 5 matrix. Okay, now I'm focusing on these 4 correlations. What do they have in common? What do these 4 correlations have in common? Row 1, 2, row 2, 3, row 3, 4, row 4, 5. What is sort of alike about them? Even though they might be different numbers. What's alike about them? They're the correlations of one observation on another observation on the same person that's just one time unit apart, right? 1, 2 is the first versus the second, right? 2, 3, second versus the third. 3, 4, third versus the fourth, and 4, 5th, fourth versus the fifth. 3, 4, third versus the fourth, 4, 5, fourth versus the fifth. How does that differ from 1, 3, row 1, 3? That's 2 occasions apart, right? So what you're focusing on here are only those correlations that are 1 unit apart, the nearest ones. In other words, we're talking about correlation of one observation on one person with the next one that happened on that person, whether it's the first and the second, the third and the fourth, whatever it is, the next one. Okay, that's what you're focusing on. Now, it turns the Durbin-Watson test focuses on just these adjacent correlations. They're sometimes called serial correlations. Adjacent correlations, sometimes called that. Okay, and the null hypothesis for the Durbin-Watson test is that all these correlations are equal and equal to 0. They're all 0. That's what you're testing. That's what this test tests. Okay? And the alternative is that at least one is not equal to 0. Okay? Now, you notice that this test is just focusing on these adjacent correlations. It's not focusing on the whole correlation matrix. So you're not testing something about whether the correlation matrix is autoregressive or whether it's unstructured. You're just testing something about this. Okay? Okay, now let's suppose, let's think about this. I am watching the clock here a little bit, but let's think about this, and I'll continue a little bit after we take a break, but I want to talk a little bit more about it. Let's say you did this test, and there's a way to do this test. Let's say you did this, and there's a program to do it. You do this test, and it's not significant. Let's say it's not significant. Suppose that happened. What will that tend to tell you? What might you think that you should say? I didn't hear. Somebody mumbled something. I don't think it was Kate, but I'm not sure. Yeah. You might think that if the adjacent ones are all 0, then any correlations further apart are probably even less correlated, right? So if these are all 0, maybe you think all of them, all these correlations are 0. It's not testing that, but that's what you're testing when you do this. Get that? So that's why people like doing this, okay? They like doing this. So it doesn't test for everything else, but this is the only test that was available until recently. We're going to learn about something else, which is used in ProcGen GLIMMEX, which is called a Cove test statement. But this is Durbin-Watson test, okay? So, so that's a reason for doing the test, because it's a way of saying, well, maybe this is a way of deciding whether I've got independent data. It's not the only way to do it, but that's why people use it as a sort of a overall first approach to doing that, okay? So now I've got an example. This test can be used for whether you're dealing with linear models or nonlinear models. And at the end of the course, after starting next week, we're going to start talking about the nonlinear models, okay? And for this particular example, I've illustrated a version of the macro that considers a nonlinear model. And you notice it says, you may notice that where it says link distribution Poisson. So this is actually a model that's a model that involves Poisson regression, nonlinear model. You learned about that, but maybe it allows for repeated measures. Okay. In fact, what this is a test where there was a hospital, and I mentioned this, I think this example maybe in the first class. There was a hospital somewhere, I don't know, I think it was in Baltimore, and they were looking at MRSA rates, MRSA infection rates from 1 month to the next. And they followed the hospital for 88 months. So they had 88 rates, okay? And one of the questions was, have the rates changed between the first month and the 88th month? In fact, there was an intervention done somewhere in the hospital at the 25th month to try to get people to be more careful in terms of how they dealt with their patients so they wouldn't get infected. So there was an intervention thing. And that's what this model is intended to do. But what I'm illustrating, though, is an example of this macro that allows you to do a Durbin-Watson test. And you notice that somewhere when you do a macro, you see this thing where it says percent include? What's that? You've already used the colin macro. Percent include is a statement you have to tell the computer where the macro is located on the computer. So that's what this does. And then after you write, now you notice it says ProcGen mod. Why didn't I write proc mixed? Because the outcome variable is now a rate. It's not a continuous variable. So I had to use something else. We're going to talk about GenMod. We haven't talked about it yet. So I'm using ProcGen mod, okay? Now, then I write the model statement, which has three different variables. One's time, one is some indicator variable, and another is some other variable related to time, but it's time after after the intervention is what it is. And then it's got a bunch of stuff, and then you see where it says %dw, and then it's got some stuff here, written over here. This %dw and what's written over here is the thing that invokes the macro. This tells the computer where it's located. This runs the macro. Just telling you what this did. Okay. Now, there is a problem with this particular example. This particular example is illustrating a data set where there's only one cluster. What's the one cluster? What's the cluster? I just described it. What's the cluster? The cluster is the hospital. How many observations were in that hospital? 88. Were there 5 different hospitals? Were there 88 observations on one hospital and another 88 observations on the second hospital? No. So there was only one cluster. So this macro, the macro that I originally had for this, and I had it up until today, believe it or not, that I only kind of knew about that was available today, was the macro for one cluster. When you run this macro, I get some output. Now you notice over here, down in the middle over here, it says observation 1.66833, and it says DW. What does DW stand for? Durbin-Watson, very good. You know, I knew you could answer that one. All right, Durbin-Watson. So if you run this macro, you get a certain statistic, a certain value. Okay. Then what you have to do with that value is you have to go to this. It's not a test statistic that's chi-square. You have to go to a table that tells you what to conclude about whether there's a positive correlation, whether to accept or reject the null hypothesis. This is neither accept or reject. This is accept, and this is reject the negative. This is reject the positive. So you have to go through this thing to do it. Now, it turns out that when you do it in this case, you notice in this example, there were 3 variables in the model, right? 3 variables in this model. What were they? 3 variables, time, this I variable, and this TS variable. So K was 3. N is what? What is N in this case? 88 was the number of time points. It was the number of repeats, okay? And now what you have to do to use this table is you have to go, see where it says significance points? Okay, now N was 88. N was 88. Where is that here? It's like close to 90, right? Okay. What about, what was K? K was 90, and then K was 170. K was 3, so it's 1.59 to 173. That's what you do. You look at those 2 numbers, then you make a decision depending upon what the rules were that's described over here, whether you've got something significant or not. That's how it works. You know, it's a little weird. I mean, you'd like to be able to say it's significant with the chi-square, but you don't do it that way with this table. When you go through this, it'll turn out that you will find that this is a borderline. Accept or reject is computed. You got a borderline. D lies in the D is 1.66. It lies in this interval. So neither accept nor reject. That's borderline. If you neither accept nor reject, borderline. That's what that means. Neither one. You know. So that's what you're getting, a borderline decision for this example. But now there's a problem with this. Problem with this is that one cluster. Okay. So what do you do if you have more than one cluster? That's the question. Okay. Well, until about 2 hours ago, there wasn't a program available. But 2 hours ago, my colleague, co-author of several books, who? Eli or Mitch? Actually, I tried to get Eli, but he was in jury duty. I think he was. At least he didn't answer. I tried to get Mitch, and he wasn't. So Mitch wrote an updated macro for clustered. And the macro is now there. He did it within the last 2 hours. And we sat there together. So you now have something you could do. Now, that should work for this when there's one cluster, but it should work for, now, when do you have, let me show you something. Let me show you something. See, it says Durbin-Watson test for several clusters. Now, there's a term in the statistical literature when you have more than one cluster. That's sometimes called panel data. The panels are the different cluster. You've got one cluster is one panel, another cluster, it could be different people, but could be just one person and another person, different panels, but it's panel data. Turns that Mitch wrote this macro. And what we did was, now look at, there's another table for this macro, but look at what is on this slide. Then I'm going to stop, take a break here. But look at what's on this slide, then we stop. Now, what have I done here? What data set am I running? Can you see? The FEV data set, right? The FEV, because you see, FEV, 40, I'm just, and what I'm now doing is, I said percent include. Now this macro on the computer it's in the, I'm going to put it on the, I haven't put it yet on Blackboard, but I'm going to put it on, it's on the S drive. But I'm going to, it's called the Durbin-Watson macro, panel macro, as opposed to the Durbin-Watson macro, you might say over here, it was called the Durbin-Watson macro. Now I've got the Durbin-Watson panel macro. Okay, and then I plug in some information, and then I put in, this is telling the computer where it is. This is telling the computer what I have to do to get this Durbin-Watson test. Okay, and you notice that, you see it says PRED, FEV, PRED, and then week. I have to put these four, now the PRED is telling the computer what the data set I want to base this thing on. And the data set, you see where it says output PRED? What's that? What have I done here? What have I run? I've run proc mix on the FEV data set, and I've got an output, and that's the PRED. That's the predicted values and everything that goes with it. That's the output. Okay. And then I'm saying with that output, that's the data that I want to use, and relates to the error terms and the residuals in those formulas. And you see the FEV is the true FEV score, the actual observed FEV score, and the predicted is the predicted FEV score. And the week, it has to do with the, remember, for the FEV data set, the week variable is the variable that says everybody had 5 weeks. So you have to put that in there. And then you run this thing, and lo and behold, you get this answer. Just showing you the answer. That's the Durbin-Watson statistic, 0.65887. Is that significant? So you have to go to tables of the Durbin-Watson test. Now, the table that I showed you that I used to do it for that MRSA data set was the table that you used for one cluster. And if I use that table here, I wind up getting this conclusion. See what it says? Reject H0 for positive, or what am I concluding? This is for the FEV data set. What am I assuming about the test for whether there's serial correlation? What does that statement say? It says yes. It looks like there is significant correlation. Well, you might imagine that because that's the way the data was set up in the first place, so that it looked like there were, so you get significant result. Now the problem with this result was that I actually used the table that was in the original paper that described the one cluster Durbin-Watson test, not the panel. And there's a paper that does the panel thing, and that paper that does the panel thing has a different set of stuff, which I put into this slideshow, which you can use to make your decisions. I'm not going to do that here, but it turns out it has to do with, you see H50? H stands for the number of clusters. How many clusters are there in the FEV data set? 40. So that's the closest thing. See, it's 50, 100, 150, 200. Okay. T stands for the number of variables in your model. Okay, in that model, the number of parameters in your model, there was beta naught and 4t. So t was 5, but this is for t equal to 6. That's close. This is t equal to, the next one was for t equal to 10 over here. So I'm just trying to get an approximate thing. And then it turns out n, wait a second, I'm not sure. Actually, t is the number of time points. There were 5 weeks, and this says 6. N is the number of parameters, which is 5. And so where you would go in this table is you'd look at these two numbers to make your decision. And it's not that, it's different two numbers, but if you look at these two numbers, you're going to come up with the same conclusion that I concluded when I used the other table. So all I'm saying here is, and that's when I definitely have to stop, we need a break. What I'm saying here is that there is this test, the Durbin-Watson test. It's a test for serial correlation. It's a test that makes sense. We now have a test that considers panel data. It works. Checked it out. And you could use it when you want to assess something about correlation structure, but you're going to learn something even better after the break. Not after this break, but after we have the spring break. Okay, so stop now. It's 4 o'clock. Let's come back at 4:15. I'll still give you 15 minutes. And I got a few other things to do. Okay, a few other things is to actually talk about the main topic for today, and then to talk about, have Tiffany's group do something. So I haven't forgotten you guys. You're going to be there at the end, but, okay? So here you go. So that's a new thing, okay? Durbin-Watson test. How many understood it? How many can do it? Well, until you actually look at the macro and set it up and do it, you can't do it. But that's why it's there, okay? So, okay. 4:15, okay? Okay. So we're ready to continue here. We're now ready to start the transition from linear models to nonlinear models. Okay, and the most initial way to do that is to talk about what are called generalized linear models, which is the first sort of way to see how you can do something like that. And you already know something about that, even though I don't know if that terminology was used to talk about generalized linear models, because last semester you used a program called GenMod, right? Did you? Do you remember doing that? Okay, I'm not getting, okay. You use GenMod, okay, and what did you use GenMod to do? Well, you used it to do Poisson regression. Remember? Used it to do Poisson regression. You might have also learned at some point that I think Eli might have presented, GenMod also lets you use logistic regression. And the key way you use GenMod to do Poisson regression is you have to tell the program code when you're writing a GenMod statement and you're stating the model, you have to tell it something called the link function. Remember that? And when you're running Poisson regression, what was the link function? Log. Because a Poisson model was a model where the log rate was linear. Remember that? Poisson model, the log rate was linear. Okay. If you were using GenMod, which you may not have actually done in 740, but you could have, using GenMod to do logistic regression, well, you know, you were using mostly ProcLogistic to do logistic regression because you didn't have to use GenMod. But if you're using GenMod to do logistic regression, the link function wasn't the log link. What was the link function? It's called the logit link. Remember? Because you remember about the logistic model? The logit of P over 1 minus P was linear, right? The logit of p over 1 minus p, the logit of the odds, the log odds, was the logit of p, which is the log of p over 1 minus p, is linear if you're doing a logistic regression. If you're doing a Poisson regression, the log of the rate is linear. Okay. So when you're talking about a generalized linear model, you notice both those examples were examples of a situation that even though the model was more complicated than linear, you can get out the linear part. There was a linear part of the model that you can get out by taking a certain transformation. And that transformation was called the link function. If you use the logit transformation, you'd get the linear model for the logistic model. If you use the log transform, you get it for the... So generalized linear model is a general form that allows you to put a lot of different models together in one framework. And that's what GenMod does. GenMod is a general program to allow you to use generalized, to fit generalized linear models, but it's even more general than that because it allows you to consider models where you got correlated data. When we talked about Poisson regression, for example, last semester, we weren't talking about correlated data. We just had Poisson. We had a person who had a count, another person or had a rate, another person had a rate, and we had independent data. But if you have a person that's measured, the rates are measured several times, and another person, the rates are measured several times, then you got correlated data. And GenMod allows you to deal with correlated data in addition to just independent data. So anyhow, so a generalized linear model is important because it provides a framework that allows you to consider a whole bunch of models in one common framework. And you've already sort of done that, and I'm just going to talk a little bit about it and where it fits in and where you go next. And where you go next is to talk about quasi likelihood. Now, if you talk about a generalized linear model, there are three parts or three components of a generalized linear model. A random component, which has to do with the distribution of the outcome variable, the variable of interest. If you're talking about a continuous variable, the random component is often assumed to be normally distributed. If you're talking about a binary outcome, then the random variable is often considered to be either binomial or sometimes called point binomial because it's either 0 or 1. If you're talking about a Poisson variable, Poisson regression variable, then the outcome variable, the distribution, is usually considered to be Poisson. Okay? So the random component is whatever you think the distribution of that outcome variable is that you're talking about. Okay? The systematic component refers to the right side of the model, refers to the side of the random component refers to the left side of the model. The systematic component refers to what goes into the right side of the model. And the way the right side of the model is written for any generalized linear model is that there's a part of the right side of the model that's linear, that you can get out with a certain link, with a certain transformation. If you're writing a linear model, well, the right-hand side is all linear. If you're running a logistic regression model, well, the right-hand side isn't linear, but it's 1 over 1 plus e to the minus a linear, so there's a linear part, okay? So when you talk about the systematic component, you're talking about the right-hand side, and you're talking about the part of the right-hand side that's linear, that you can flush out by taking an appropriate link function. And the link function is the thing that allows you to go from the random component to the systematic component. It links the two together to define the model. That's what it is. That's all it is. Okay. And so now, the literature on generalized linear models, the original literature, and I've got some papers that you could read or not read that talk about it. The original literature about this says, well, just like we talked about for Poisson, we did Poisson analysis in last semester, the literature says, well, you can talk about generalized linear models even if all the data is independent. We had Poisson analysis and we didn't have repeated measures. You can talk about independent binary data, and you could use GenMod with a logit link and run that. You can even go further and go to deal with correlated data by generalizing generalizing a generalized linear model to allow for correlated data. But the original literature, particularly in the paper or papers that I think there's one paper that you could read if you wanted that talks about this, assumes everything's independent. And if you want to generalize the correlated data, then you're talking about GenMod, and you're talking about something else that we're going to be starting to talk about next week is GEE. What's GEE? Generalized estimating equations, which is what GenMod does, GEE. It deals with correlated data. Okay, so what is GLM? It refers to a class of statistical model, I'm just reading this, representing a natural generalization of classical linear models. It's a natural generalization. There's a part of the model that's linear. That's why it's a generalization. And special cases include linear, logistic, and Poisson. Okay? Generalized linear model is a general framework, and the three things that we often do when we're doing epidemiologic studies are these three, but there are others. Okay? And again, to define a generalized linear model, we must specify the three components. Okay? Now, on this slide, I'm saying a little bit more about each component. Okay? I already said something about 2 and 3. The systematic component is something that talks about the linear part of the model, and the link function is the thing that links the random to the systematic component. So I want to say a little bit more about the random component, the random component. If you've got a variable that you're measuring in a study, that could be independent data. That's the way it usually is for the original paper, but it could be correlated data. If you're dealing with normal or normally distributed or binary variable or something, there's a general distribution that if the variable comes from a generalized linear model, there's a general distribution that you can say this variable fits within, and it's called the exponential family of distributions. It's a family of distributions that includes several ones that are very popular, like normal, Poisson, binomial, and all of that. Okay, so that's what the random component is. Okay, so now let's go a little further. Now, why is GLM important? I've sort of already said. It allows us to exploit the common attributes of several seemingly different regression procedures so that these procedures can be studied with a unified theory rather than as an unrelated collection. These procedures are related to one another. You can do correlated data or even non-correlated data analysis using the generalized linear model because they're special cases. It's applicable to both discrete and continuous response data. It allows nonlinear models, binomial, Poisson. It even allows non-normal data, where it could be binary or Poisson or others. Note, however, as I say, the GLM theory requires knowledge of the likelihood function based on the exponential family and assumes that observations are independent. No correlated observations. So the original idea of a generalized linear model assumed that you had independent observations, and you knew you had an outcome variable, y, that's your outcome variable, and you knew the distribution of y. You knew the distribution of y, and you could therefore, and that y comes from an exponential family, but because you knew the distribution, you could do maximum likelihood. You remember what you did for maximum likelihood? What did you have to do? You took a likelihood function, you had this likelihood function that was a combination of the data and the model that you were doing, and then you maximized it. And how did you maximize? Well, I think I might say it on the next slide. Yeah, no, I didn't say it on the next slide. What do you do to do a maximum likelihood estimation? You remember what you have to do? You get a likelihood function. It's a complex mathematical form that involves the data and the parameters in your model. And to maximize it, in order to maximize any kind of mathematical function, what do you have to do? You may not remember how to do it, but what do you have to do? You have to take a derivative and set it equal to 0, right? You may not remember what a derivative is either, but you have to take a derivative and set it equal to 0. And when you do that, you get not one equation, you get several equations because you have several parameters that you're trying to get maximum likelihood values for. And you wind up getting a set of equations. When you're doing maximum likelihood, you get a set of equations that you try to solve. That when you solve them, you're getting the values of these parameters in your model that solve this set of equations and give you what's called the maximum likelihood estimate. That's what the maximum likelihood is, the set of equations that are the most likely values. You remember that? I mean, that's what we learned. Okay, so now, if you don't know the likelihood function, then you got a problem. You can't take the derivative of it, because you don't know it, and you can't take the derivative and get a set of equations. So that's the problem if you don't know the maximum likelihood, if you don't know the likelihood function. But a generalized linear model assumes that you know the random component. Okay, so we're going to work with that for now, and we're going to talk about the random component. Okay, now talk a little bit more about the random component. Again, the random component is talking about the y part, the outcome variable that you're dealing with, the outcome for the y sub I for the ith subject. And what you're assuming is that the distribution of y sub I comes from something called the exponential family. Okay, and what that means mathematically is that you could write what's called the probability density function. Now, some of you learned that, I know in the PhD students have learned that, what a probability density function is. Am I correct on that? I think so. I hope that by now. Is that true, Kate? I think so. I'm just looking, Monica, Michael, but I'm not sure about the MPH students, but it's basically the probability distribution. Describes how do you get a probability for values of this outcome variable. And that's the formula, that's the general formula for a variable, y sub I, coming from an exponential family. Now, this is a general formula, but this formula includes a lot of different distributions that you know, one of which is the normal distribution. So if we actually go to the next slide, and you look at this general formula, and you look at this formula at the bottom of the slide. This formula at the bottom of the slide is how this formula works for a distribution that's normal. So a normally distributed variable is a special case of this general formula. So if the variable is such that it's normal with mean mu and variance standard deviation sigma, that's what is going to be plugged into here to get what the formula looks like. So all I'm saying is that a normally distributed variable is an example of a variable that comes from the exponential family. That's all I'm saying. It's one of those variables, okay? And it's not the only one, because on the next, I've actually plugged in, I've written the two formulas again, and I've plugged in that theta I would be mu sub I. I've plugged in what they are. How you would go from this to that in terms of how it's generally defined and how it's defined specifically for the normal distribution. But also, you can talk about the random component for a binomial distribution and a Poisson distribution. The other two ones that are the most popular, it's not the only ones, it's negative binomial, there's other ones. Okay? But for these other ones, then you have to define what those terms are differently because it's a different variable, but they all fit into this general framework of the exponential family. So they all come from the exponential family. Okay, so that's what a generalized linear model includes: variables that we all like to work with, and variables that we ought to work with and eventually find out we ought to work with them. But these are the three most popular ones. Got that so far? Okay, so I'm not doing anything that fancy. Now, the systematic component of a generalized linear model refers to the linear function of the unknown parameters. That's what it refers to. It assumes that you can identify a set of explanatory variables, that you have some kind of, or covariates, denoted as x's, predictors, which combine to produce a linear predictor, which somehow is located within the description or the statement, the model statement. If it's a linear model, the linear predictor is on the right. If completely on the right. If it's a logistic model, the linear predictor is 1 over 1 plus e to the minus, and it's got that linear predictor. So it's in the model, but it's in the model in a different form. So the x's can represent any types of variables. They could be exposure, product terms, whatever it is. The x's represent covariates, they could, and the x's are typically assumed to be measured without error. That's what you usually do when you run a model, although there are complications that you sometimes do, and like putting in random effects, but we're not doing that here. So that's the systematic component. And the link function is some function of the mean you see, you've got a variable y. Y is the outcome variable. It has a certain distribution. It has a mean and a variance. Any variable has its mean is the expected variable e of y, and its variance, okay? And the link function is a function of the mean, some function of the mean. One function of the mean is just the mean itself. That's a function of the mean. Another function of the mean is the log of the mean over 1 minus mu. That's the logit function. Another function of the mean is just the log. So if you're talking about, these are 3 different link functions that you could use if you're talking about a generalized linear model, okay? So if you got this kind of model, you specify the link function, then you're really sort of determining the model. In fact, you can do a little algebra with this because it turns out, G of mu stands for the link function. The link function, by the way, what symbol is this? See this thing? It looks like an N. Does anybody, I always say this every year. What symbol? It's a Greek symbol. What is it? Is it a nu? Is it a Greek nu? No. You know what it is? It's eta. That's what it is. Eta. How many knew that? I don't know. It's eta sub I is G of, this is where it's in that paper, so that people, I've just used the same language. So the eta stands for the 2 things. It stands for the link function that links the linear part of the model. It's the linear part of the model, and it's related to the mean in terms of this link function. So, for example, if the link function is g of mu equal to mu, and g of mu is simply the sum of xi beta, then mu is just the sum of xi beta. It's a linear model. Can you see that? If the link function is the log of mu over 1 minus mu, the log of that, then in order to get what the mu is, in other words, this is saying the relationship of the linear part to the mean is this, or this. In order to get the formula for the mean, you have to try to solve for mu in terms of the link function. And if you do that here, this is what you get. And you notice what you see? What do you see there? That's the logistic model. Okay? And you can do the same with a little algebra. I have a couple of slides that go into it a little bit more, but I'm not going to do it now because of time, other than say if the link function is the log of mu, then the mu is a Poisson regression. It's a Poisson regression model. The formula is, it's an exponential model, and the log of mu is linear. So what the log of mu is linear, if mu is of this form. The logit of this mu is linear. This variable is linear by itself. So these are all examples of link functions. Now, this is the Poisson link, and it's a little not worth talking about how you get this formula, but you can look at it if you want to just make sure you satisfy yourself. But now, let's look at what's on this slide. Let's look at what's on this slide. The likelihood function for a generalized linear model. Now, don't get all worked up about what's on the slide. It's horrible, right? You agree with me that it's, well, I don't know if it's horrible. You've seen movies that, what was the worst movie you've seen this year? The most horrible movie you've seen this year? To me, The Revenant was about as bad as you could get. Okay. But I also saw Son of Saul, which was difficult. Anyhow, this is the likelihood function for a generalized linear model. This is not the worst function you'll ever see in your life, but it's not that great. So you see it says pi, I goes from 1 to k, f of y sub I, theta sub I. What's the f? What's the f? What is that? That's the formula, that's the expression for the distribution of y, right? That's sort of like the probability of y, probability of getting y, or the density function for y, okay? Now, you notice I'm multiplying for one subject, this function, and then by another subject, and by another subject, and it goes I from 1 to k. And what I'm assuming here is I have independent data. I have independent data, and k is the number of people in the data set. So everybody's independent. You know, it's like I have one observation per subject, and k is the number of observations. What allows me to say this? That the likelihood function is the product of these things. What allows me to say that? This goes back to last semester a little bit, and goes back to your first course in probability, if you ever had one. Okay. The probability of two independent events is what? Product of the two. So if this is the probability for one person, and then for person I, and then you got another person, I is equal to 1, and then you got another person, I is equal to 2, and you're talking about the product for person 1 and person 2, the thing that allows you to multiply together to get the product for 1 and 2 is the fact that they're independent. You're assuming that they're different people. They're not coming from the same family, and you don't have repeated measures. So this allows you to state this. So that's the likelihood function. And then if you replace this expression by what it is, this complicated thing, that's another way to write the expression for the likelihood function. Okay. Now, what do you do to maximize a likelihood function? You take the derivative and set it equal to 0. That's what you do. I already mentioned that. Okay. Turns out when you have, I say turns out a lot. I've noticed that. My wife has been telling me too. So turns out, now I know I'm saying it. If you see this, and you want to take the derivative of this, and you've got a product term you want to take a derivative of, you may remember this from calculus, and most of you don't, but you may remember to take a derivative of a product term is a pain, because you have to consider the parts of the product term, and this with that with the other, or something like that. It's easier to take the log of the product, because the log of a product is the sum of things. And if you want to take a derivative of the sum, you can take the derivative of each component of the sum. So it's easier to take the derivative of a sum of things. So when you're talking about the maximum likelihood solution for a generalized linear model, I'm not getting that fancy. You're just talking about taking the derivative of the log of L, because if you solve the derivative of the log of L, set it equal to 0, it's going to give you, and you max it, and you get that, whatever the solution is, it's going to be the same solution as this, because the log of L and L coming from one another. So obtain the maximum likelihood solution, we must take, in order to take a derivative, and you got several parameters, several betas in your model. I'm not showing the model per se here, but you got the betas and the main variables in the model. What you do is you take partial derivatives for the L with each beta, and you set these partials equal to 0, and what you wind up with is a set of equations. You got a set of equations that have to get solved. And that's what the computer does. In Proc Logistic, in Proc Gen Mod, whenever you're doing maximum likelihood estimation, the computer is solving that. So you never see those equations, but that's where they're coming from. They're coming from taking this derivative of this and getting a set of equations and solving them. And this is what, if you do a little algebra, and I did this on the next slide, I didn't do it on that slide, do a little algebra, you can show that when you take the derivative, set it equal to 0, and do all these partials, you get this expression. This is the expression for the solutions, what are called the equations that have to be solved, and they're called the score equations. They're called the score equations, or sometimes the maximum likelihood equations. You solve these equations, you can get the maximum likelihood value. Okay, that's what this says. Now, there's something very kind of interesting to some people, but not, I don't know how many here, about this result, okay, this formula, this expression. What you don't see in this expression, even though you started out with this, what you don't see in this expression is F. F is the this complicated function. What you don't see is f. It's not in here. What do you see? See the mean of f? E of y is the mean. You see the variance. You see y. And if you have the mean, you can take the derivative. And if you have a model for the mean, you can take the derivative with respect to any parameter. So the thing about this formula that's interesting is that you didn't have to know what the f was in order to get this expression. See what I'm saying? Okay. Now, if you do have an f and you know what it is, you'll get this expression and the computer will solve it for you. Okay. And all that, that's fine. If you're dealing with a normally distributed variable, then these score equations turn out to be something I showed you on the second or third class when I was talking about matrix theory. The score equations turn out to be this. This is a way of writing matrix-wise. With the score x prime y minus x prime x beta equals 0, you solve for that, and you get x prime x beta equal x prime y, and you got an expression for the estimate of the least squares and the maximum likelihood estimate for a linear model. But the key thing I'm trying to say about this that makes it interesting, that gets me into the next topic, is the fact that what if you don't know f? What if you don't know the distribution? Or what if it's really complicated and you don't, it's so complicated the mathematics is so tough? Well, what if if you don't know f, but you know something about the mean and the variance of f for any individual, for any one individual at a time? If you know that, and you you put whatever the mean and the variance is, and you take the derivative of this with respect to, and you set up this equation, is this a set of maximum likelihood equations? If you don't know the f. Is it or isn't it? Well, it's not. If you don't know the f, you can't start this way, take derivatives, and get to this. If you don't know the f, but you know the mean and the variance of the f, but you don't know f itself, you could still write this expression without knowing f. Get what I'm saying? And this expression is a set of equations. Now, if you don't know f, and you set up this set of equations, they're not technically maximum likelihood equations. They're called quasi likelihood equations. Because you don't know the likelihood function. This isn't the score equations. This is a set of equations you get without knowing the distribution of y. You know the mean and the variance of it. So the whole thing that leads to GEE is and quasi likelihood is that if you don't know the actual distribution that you're working with because it's too complicated, or you're dealing with correlated data and it's really mathematically a mess, then you can still set up a set of equations that could be solved. And if you solve them, hopefully they're going to have properties that are similar to maximum likelihood estimates. But they're not going to be maximum likelihood estimates. What are they going to be called? What are they going to be called? They're not going to be called maximum likelihood because it's not a maximum likelihood equation. What are they going to be called? Quasi likelihood estimates. Okay? In fact, if you if you set up a set of equations which also reflect correlated data, where you know the mean and the variance of the y, but you don't know the actual distribution of the y, and you set up this equation, and you set up this set of equation, and you solve it, you're not going to get maximum likelihood estimates. You're going to get what are called GEE estimates, or generalized estimating. The set of equations are called generalized estimating equations. And the estimates you're going to get from not knowing the distribution of this complicated correlated data thing are going to be called GEE estimates, as opposed to maximum likelihood estimates. So that's what quasi likelihood is. So that's some theory you need to know in order to just get a sense of what's going on here. But you need to know something, but you don't need to know everything, and that's where I'm stopping with that. And now I'm ready to go on with the next thing on the list, and that's quasi likelihood. Quasi likelihood. We just sort of talked about that. Okay, quasi likelihood. Now, again, I got to watch the clock because I got to get your group to get up here, and I got to give you enough time to do it. So I have to get to a point where I have you do this, okay? I got it in my head where it's going to work, okay? Believe it or not. So,
You don't doubt.
what's that?
You don't doubt.
You don't doubt it, okay. By the way, I didn't tell you this. I'm just going to, this is an aside. I shouldn't tell you this, and I don't expect anything from anybody on this thing. It's taken care of. Sunday of this week is a big day in my life. Sunday is a big day in my life. I got a birthday this Sunday. Now wait a second. How old am I going to be? That's the question. How old am I going to be? Am I going to be 50? You know I'm older than 50. I mean, my daughter is 46, so I'm older than 50. Okay? And I got 2 grandchildren. So how old am I going to be this Sunday? 75. 75. Wow. That's 3/4 of a century. Now, Sunday hasn't arrived yet, so I haven't made it yet. You know, but I just thought I'd let you know. You know. And I don't know whether I'll even finish this class, but I'm going to try to finish this class and let you do that. So at least, you know, I can get to tomorrow. Okay? Okay, so 75. Okay, so let's talk about quasi likelihood. Okay. So what's quasi likelihood? Now, quasi likelihood, like generalized linear models, assumes independence, but you can generalize it to GEE. Okay. Now, it considers independent responses in which the distribution of y is either unspecified or unknown. Just like I said, if you don't know it or you're not specifying it, that's what we're talking about, a bunch of y variables, a bunch of outcomes where you don't know the distribution. Now, in maximum likelihood estimation, you do know the distribution. The distribution assumption is made, and the likelihood function is formed, and then you get up a bunch of equations called the score equations or the maximum likelihood equation. Now, quasi-likelihood is an extension of maximum likelihood that gives you a set of equations, but they're not maximum likelihood equations, but they look like them. They look like the maximum likelihood equations because I just showed you that on the previous slide. And that's why they're often called score-like equations. They're not the score equations. The score comes from maximum. They're called score-like because they look like it. They come from that somehow. And they're formed by using the means and the variance. Now, in order to have this set of equations, you have to know, even if you don't know the distribution of the y variable, you have to be able to know the distribution of the expected value of y and the variance of y for any given subject. You have to be able to write it. You have to be able to write a formula like that. Okay, and I'm trying to avoid saying it, the variance part of this formula is written like this, is equal to phi times v of mu sub I, where phi is a scale parameter. It doesn't depend upon y or I. It's something that's independent of the individual. And v of mu of I is some function of the mean. You have to be able to, now this is a little weird. The variance of y has to be some constant that's independent of I times some function of the mean. Now, does that work for some of the standard distributions that we know about? Well, let's look at I think it's the next slide. Yeah, here's the next slide. Suppose you've got, let's look at, before we look at number 1, let's look at number 3, Poisson variable. Okay, you remember you learned about a Poisson distribution, that the mean and the variance is the same? Poisson distribution, the mean, the E of y, and the variance of y are the same values. So if you're talking about this formula for the Poisson, phi is equal to 1, and v of mu I is just mu I. So that fits. Poisson variable fits. Okay. What about a point binomial? You're talking about a logistic model. Okay. A logistic model, the variance of mu, remember the variance of a proportion is p times 1 minus p? P times 1 minus p over n. But if n is 1, if you're talking about a point binomial for one person, 0, 1, you only got one observation per subject, it's p times 1 minus p over 1, and p is the mean. So it'd be mu times 1 minus mu over 1, so that's the variance for a binary, a point binomial distribution, which you're talking about a logistic model. And so phi would also, this fits. So this fits too. And then there's this little trick. How does the normal distribution fit? Well, the normal distribution fits because it's a little trick here. Phi is the variance. And the function of the mean that goes into this formula is 1. This also fits. So the normal, the point binomial, and the Poisson all fit for a given subject this requirement to have a quasi-likelihood situation, even if you don't know the distribution, if you have it normal. Get what I'm saying? So that's what I'm saying, okay? I'm still watching the clock here. Tiffany? Okay, now using quasi-likelihood assumptions, a system of score-like equations can be specified and solved by computer iteration. That's what I've already said. You can set up those equations that are like the score equations, but they're not the score equations because you don't know the f function, the function of y, the distribution of y, but you know the mean and the variance. So you can set up, and the solutions, which are called quasi-likelihood, have essentially the same asymptotic normality properties as the maximum likelihood. That's the nice thing about it. You have this set of equations, you solve it, you get an estimate of any parameter in your model, a coefficient of an exposure variable. And you could say that if you have the sample sizes large enough, that beta hat is approximately normally distributed. That's what you can say. And that allows you to go to do a test, a wall test, right? Beta hat over the standard error allows you to get a wall test. Does it allow you to have a likelihood ratio? What is this? However, likelihood ratio tests are not possible from quasi-likely tests because log likelihood functions are not available. You don't have the likelihood function. You can't get the log likelihood. You can do a wall test, but you can't do a likelihood ratio test. So what I say here, the statistical inferences, there are actually 2 kinds of tests you can do. You can do a wall type test, involving quasi-likelihood estimate and their standard errors, and you can also do something called the score test. There are 2 tests, wall test and the score test, okay, that you can do if you're doing quasi-likelihood or you're doing GEE, which goes generally into correlated data when you're allowing for non-independent observations. Now, you remember when we talked about the logistic model, what test did we talk about for the logistic model? If you're doing a test. If you're doing a test, and I'm still watching, I got time. Doing a logistic regression model, what were the tests? It's wall test, that was one thing. What was the other test? We talk about a score test? We never did. There was one, but we never did. We talked about a likelihood ratio test and a score test. What do we say about that? Well, you can do them both, but they may not give you the same answer, right? Is that what we said? And what do we say if they don't give you the same answer? Which is better? Likelihood ratio is better because? From theory, some statisticians showed it was, you have to grant some, likelihood ratio is better from statistical theory. If you get different answers, go with the likelihood ratio test. But now, you're doing quasi-likelihood, you can't get a likelihood ratio test, but you can get a wall test and a score test. So you can't use the likelihood ratio. Which of the 2? Well, theory shows that the score test is better. So if you have a choice between the 2, you can do them both. They might give you the same answer, but the score test is better. Now, when you're using programs that deal with correlated data or quasi-likelihood data, correlated data, and you're doing quasi-likelihood, then the programs are not going to give you a likelihood ratio test. But the programs do allow you to get wall tests and score tests. And when you're allowed to get wall tests and score tests, even though the answers might be very similar, if the answers are different, you go with the score test. That's what I'm saying. That's all I'm saying. Okay. Now, in the rest of this, I also said score tests are preferred to wall tests based on statistical theory, although results are often quite similar. Both score and wall tests are easily computed in SAS procedures, GenMod and GlimMix, which you're going to be learning. GlimMix also allows something else called pseudo likelihood ratio tests, which we'll get to up at some point. That we may not be important, but something that we'll get to. So now, from this point on, I talk about some theory. I say, well, this is what the score equations look like. Okay. Well, I already said the score equations are a bunch of equations that, based on the mean and the variance formulas you put in, the computer solves it. So these programs solve it. So I'm not going to focus on that. If you want to compare quasi likelihood with maximum likelihood, this slide shows you some differences. With quasi likelihood, you don't have a likelihood function. With maximum likelihood, you do. Well, okay. Why is quasi likelihood important? Because it allows relaxation of generalized linear model theory to about just exponential families. You don't need an exponential family. It allows situations where the underlying distribution, the corresponding likelihood function, can't be easily specified or is unknown. But at the same time, it provides estimates of model parameters that have properties similar to maximum likelihood estimates. So it's great, you know, for something that couldn't easily do. So that's why it's important. Okay. Now, you can do hypothesis testing for both. You can do, as I said, there are two ways you can do testing, walled and score tests. And the rest of the slides in this PowerPoint presentation talk about how you can do the walled test. Now, these are two formulas for the walled statistic and the score test. And the rest of the slides go through the theory on where these formulas come from. And you notice that these formulas involve matrices. So if you want to consider the general way to do either one of these tests, you have to use matrices to do it. So if you want to understand that, you have to read through the rest of these slides to do it. And 99% of you, or maybe more, don't care about that. Some of you that might want to do something more theoretical might want to read through this thing to just get a handle of it, but as far as I'm concerned, I'm not going to do that. So there's a whole bunch of things in here where I talk about the wall test and the score test, but I'm done. Okay, that's why I knew I was done. Okay, and you don't need to know that, but if you want to, they're there. Okay, I've put it in there. I've written that stuff for you. Okay, so you can or not. Now, if you're a PhD student in epidemiology and you're going to come and you're going to have to do a qualifying exam, am I going to ask you something about this? Well, I don't know. I haven't thought about that. You know, if you're an MPH student, you don't have to worry about that. A PhD student, you probably don't have to worry about it either. You know, but anyhow, so, but that got you nervous, right? I knew that would get you nervous, right? Back there too, right? So, okay, so Tiffany, we're ready for you, okay? So what I'm going to do is, that's 5 o'clock, so we got plenty of time, and I'm going to get out of this. I'm going to get out of this, get out of that. I'm going to stop this.